This is for questions 46 through 49. It asks what type of orbital, let me see if I'm reading this right, does an electron with the following quantum numbers occupy? So I didn't actually write that verbatim up there. But the way you see it written on the test is much better wording. What type of orbital does an electron with those quantum numbers occupy? And the options are A, a 3p plus, B, a 3dz squared, C, a 3s, and D, a 2pz. Wait, a 2pz, or is that 2pz? Okay. Now, this one's pretty straightforward. The principal quantum number 2 means there's what are the options here? Which one of these has to be the one? Yeah, there's the only one with the principal quantum number 2. But let's go on ahead and see just for fun. L is equal to 1. L equal to 1 corresponds to what? Some sort of a p orbital. And the fact that m sub L equals 0 means the actual projection of the orbital angular momentum onto the z-axis is 0, corresponding to which axis did we arbitrarily decide to be the one that's the reference axis? The z-axis. So the pz has m sub L equal 0 because its projection onto the z orbital axis, onto the z-axis, this being x, y, and z. If I were to project the angular momentum, in other words, if I were to take my fingers and place my wrist in such a way at the origin and push my fingers towards the electron density and then swing that electron density around, the axis is going to lie, that I'm rotating about, is going to lie in the xy plane and has no component in the z direction. And so it corresponds to m sub L equals 0. A better detail for the orbital angular momentum can be found in the handout that I gave you on that. Which, but anyway, that is, so that one we can clearly make is, what did we say it was? D. It was pretty easy to decide just on the basis of this too. That was a good, that was revealing. That was the only one with a principal quantum number 2. Now, for the next one, for the next remaining 3, they're all principal quantum number 3. So I have to look at the L. If L is equal to 0, what kind of an electron, what kind of orbital is it? It's an s orbital. It has 0 orbital angular momentum. And m sub L has to be 0 as well. So it's got a 3s. That's option what? C. Now, for n equals 3, L equals 1 means what kind of an orbital? It's a 3p, but m sub L equals plus 1. Oh, well, G. That's the 3p plus. That is something, again, you will only get out of the detail of the handout for the plus and minus orbitals, because, okay, 1 second. So that is 3p plus, that's the A, and that's because p plus, the z quant, the fact that we've chosen the orbital angular momentum, the square of the orbital momentum commutes with the Hamiltonian, and the z, all of the components of the individual components of the angular momentum, the x, y, and z components, commute with the square of the total angular momentum. So we've arbitrarily chosen the z to be the one we'll use as a reference. So it's the z component of the angular momentum. Now it turns out that the x, y, and z components of angular momentum do not commute with each other. So once we've decided that z is the one, we can say nothing about x and y. And instead we have p plus, which is defined as px plus ipy and P minus, which is defined as Px minus I P y, where the I is the root of imaginary numbers. These are actually, these commute, or these have real quantum numbers. This is m sub L equals plus 1, and m sub L equals minus 1. And this one doesn't look like, they no longer look like those orbitals with the dumbbells. They look like donuts instead. And you saw them in the free atomic orbital handout. So the P plus is a donut that is rotating in this direction, P plus. And you can see inside it and the P minus is rotating the other way, P minus, and it has, so this has angular momentum, this one rotating this way has a component of angular momentum that goes in this direction. This one has angular momentum going in this direction. And this is the Z direction here. So it's Z component of orbital angular momentum. This is plus 1, this is minus 1. So that explains those quantum numbers. You don't need to worry about drawing these. It's just for your personal background that I have it. And so you get a more complete understanding. These are not useful for constructing molecular orbitals, but they are for the free atomic states. And that's why I include them. Okay, now, last but certainly not least, N equals 3, L equals 2. What's L equal 2 correspond to? A d orbital. M sub L equals 0 means it's the only one we can say for sure, the dz squared. So it's the dz squared, 3dz squared, which obviously we're out of options here anyway, but I want to draw the dz squared because I'd love to draw this one. M sub L equals 0. It has 0 component of orbital angular momentum in the z direction. Okay? So that answers that cluster. Is everybody clear on this? Okay. So if that clarifies that one, that's a wrap.